So I think we can start our talk. So hi everyone, I am Sagar. I am a PhD student in Astronomical Observatory at University. So this is our public um, astronomy outreach talk by our astronomy population team in Astronomical Observatory. So this is not stuck like so our name is team's name is Night and the Stars. So yeah, so I'll be talking about the impact of astronomy on society, basically some technological advancement that have developed in astronomy, and it is really useful in different parts of science or maybe even if day-to-day lives also. Yeah. So here is our team. We all are PhD students, and some of them are even staff members in our observatory. So we this is our beautiful observatory. So we can't do our offline talks and offline outreach program due to this pandemic. But yeah, we prepared some talk every week, almost every week, um, to present online. So yeah, so so before going to start into the topic, let's go through some basics. Maybe those things maybe require in my future slides or maybe coming slides. So this is how we see an object, how light is reflected from an object, and it is coming to our eye. So our eye is an electromagnetic detector which can see the electromagnetic radiation coming from the object, and that's how we can see an object. So this is some basics about the wavelength and the frequency of a wave, because light is also an electromagnetic wave. So yeah, and so now coming to the electromagnetic spectrum. So because our eye can see only visible spectrum, which is consists of 7 color Behavior, which we call as the visible spectrum. But apart from that, there are a whole range of electromagnetic spectrum is present in the electromagnetic realm. Those are from low frequency radio waves to the high frequency gamma rays. So yeah, so there are some examples of where we are using those frequencies or different electromagnetic spectrum in our day-to-day life, or maybe in our labs, or in different parts of our maybe life and everyday life. So yeah, human eye can only see this much of spectrum, which is optical. I think this is all about basics. Now so this is another basic, that how our atmospheric window to the electromagnetic spectrum, because if you see here, the opacity, how much the electromagnetic wave is coming to earth, and if you consider this is the ground level of the earth and this is the sky, so you can see that only some part of radio and visible spectrum and some part of even if infrared can only penetrate the earth atmosphere. Other ones are not or cannot penetrate the earth atmosphere. So yeah, so now coming to our topic, the impact of astronomy in our society. So basically this talk will not be any technical. It will be just some more brief discussions about how it is affecting our technology and different parts of science. Yeah, so throughout the human history, we are looking at the sky, and by looking at the stars, we are navigating through the oceans, we are navigating through the forest, and we are trying to connect our um, uh, connect our society to the stars. And there are so many cultures who adopted the astronomical observations, and they have done some astronomical observations, and they made like weather forecast, or maybe how the path of the sun or path of the moon and path of the earth is rotating, or they are just how cosmic objects are really moving in the space actually. So the first we thought that earth is the center of the universe, but later when Copernicus claimed that earth was not the center of the universe, and this really triggered a new revolution. And this a revolution which is throughout the humankind, and also the religion also, even if it really changed the science and society as well. So astronomy really always had a significant impact on the on us, how we perceive our world, or how we perceive the universe. So now our understanding is progressing bit by bit, and there are so many technological advancement in different fields of science, even if technology, and even if astronomy also. Now we are reaching to the farthest known to the universe, and we are looking through the higher redshifts, and to the deep into the sky, and yeah, and different types of objects are still discovered in the astronomy. And I can say this is one of the golden age of the astronomy, because where still in the space the stars are burning, and there are galaxies with full of stars, and they are really radiating good amount of radiation, so that we can see them. We can see them through our telescope, through our naked eye, through our observatories. But why do we do astronomy actually? Why it is important? Why we should fund astronomy rather than because we really have other problems in our world, like there are global warming, there are hunger problem, there are so many other problems, so many social problems, so many political problems, so many religious problems, so many things are going on. But still, why we have to fund on astronomy? I believe astronomy is one of the fundamental science in the field of science, because something which is related to the fundamental, because the universe, because we are inside the universe, and we made up of the some elements, because and those elements are created in the heart of the stars, and and how can I say, and we have to know that, not we have to, and this is a human tendency, that to dig out the questions, how old are we, what are the fate of the universe, are we alone in the universe, and where we came from, when the time started, when the universe started, and those things. So in briefly I can say only one thing. So this is the thing, that preserving knowledge is easy, transferring knowledge is also easy, but making a new knowledge is neither easy nor profitable to the society in short term. The fundamental research proves profitable in long run, and as importantly, it is the force that enriches the culture of any society with a reason and basic truth. Because yeah, that the quote suggests that, yeah, always the fundamental research is not profitable, or not any good amount of application on the society in short term, but but it has a really profitable to in long term. So we will discuss some parts of those thing in next slides. So first, coming to the part imaging. Okay, I will cover only maybe 2 and 3 parts of the technology, like imaging, then medicine, then some other parts of the some other parts of science, and how in day-to-day life astronomy is impacting our society. So in the field of imaging, now we have good cameras. I think in every mobile we have camera, and if you have a camera, there are sensors which is capturing photons and converting to electron, and then that is detected as a signal, and that is creating your image on the photographic plate, or maybe CCD, or maybe CMOS sensor. If you see here, in 2020, that's over 1.4 trillion photographs were taken to the entire humanity. And yeah, if you like, this is statistic from a website I have taken. So if you see here, it's really growing, and I think in last decade the technology of imaging is really advanced, and it is still advancing, and we are going new technologies. So how imaging is related to astronomy? So you see that the good thing about the I think not good. Astronomers are always planning to build some telescope for at least 15 to 20, 15 to maybe 10 to 15 years to run, and they always require a cutting edge technology for a new or maybe a new extraordinary technology, because in astronomy we are always looking at the sky, and those objects, the stars and galaxies, are really far away, and we really need good sensors or good cameras to photograph those things. And that's why the imaging technology is really fastly developing in the astronomy sector. So now I think you all have known this. Maybe you must have seen this in your childhood, and you have memory. Maybe you have photographed with those films. So this is the Kodak technical pan film, and yeah, and it is capable of recording the extreme fine details, and its sensitivity curve is extend towards the radar side of the electromagnetic spectrum. And in particular, this film is sensitive to the light emitted at the 656 nanometer, which is H alpha emission, which is in the visible spectrum. Like when you are looking through the sky, you are basically looking to visible spectrum, but how to record it? So that was the challenge at that time in the maybe 1960s or 1950s, when they are start to take photograph of the sky. So this was originally created by solar astronomers to record the surface structure of the sun by avoiding the sky, because sky is the blue, because the sky is mostly emitting in the blue. That's why this technical pan films efficiency is lying near the radar part of the electromagnetic spectrum. So yeah, so now you think that what is the big deal about this technical pan film, but when you think at that time, when there were no CCDs, no CMOS sensors were developed at that time, and if you really think, this technology is fast taken over, or maybe fast applicable on the astronomy field, and this is an image which is which is a comet that was taken using this film. And the important thing is you can see here the prominent structure of this comet, and that was taken over this Kodak film, Kodak pan film through a camera. So now moving to the next part. Again, we know that after those type of cameras, we got digital cameras, which is now still most widely using, but the sensors are there are the CCDs or maybe CMOS sensors. So yeah, so CCDs are charge coupled devices. So so shortly I will tell about the CCD. So CCD is a metal oxide semiconductor, or those are made up of MOS capacitors. Are basic building blocks of the, like, those are the basic building blocks of the those CCD. And if you see, every CCD is sensitive to a specific range of the wavelength, because which is corresponding to a specific range of the energy, so that it can detect that part of the electromagnetic spectrum, or maybe that part of the wavelength, which we can photograph in our mobile, or in maybe computer, or maybe printer, or anything. So the major development, the CCD was discovered in maybe 1970s by two famous physicists. They got Nobel Prize in 2009, actually 2009, for the discovery of CCD, because this has a wide application throughout the globe. If you have a mobile phone, it is inside your camera. If you are watching this video by your laptop, or maybe in a mobile, or maybe anywhere, if that contain a camera, then there must be a CCD, or there must be a CMOS sensor. So the CCD was first used in astronomy in 1976 to capture astronomical images, because we need good resolution and obviously good efficiency to detect photon, because it's coming from the far. And the improvement in popularity of the CCD is attributed to the NASA's decision, when they decided they will use a super sensitive CCD technology on the Hubble Space Telescope. I think we all know about the Hubble Space Telescope. It is the most successful science mission that ever done in human history, because it revealed so many mysteries of the cosmos, and which is really answering so many mysteries. So within few years of discovery of application of CCD to the astronomy, it is popularized in the entire globe, and it is now everywhere, in webcams, in mobiles, in personal cameras, in laptops, and everywhere. Yes, and even if we are using in astronomy. So this is that CCD sensor that was used. So that was used in Hubble Space Telescope, which is the Wide Field Camera 3, and it is still working. And the spectacular images we have seen from the Hubble telescope in some websites, or maybe some social media, or maybe some magazine, or some astronomical journals. Those are taken by some of them are taken by this CCD. Yeah. Now coming to the part medicines. So the application of astronomy to the medicine are quite vast, but from improved diagnostic techniques to the enhanced image processing. Radio astronomers are constantly struggling to see objects that are ever dimmer and farthest away in the cosmos. Similar thing in the medicine is the researchers are struggling to see through the human body, because those are obscured by the muscles, and so that came into the picture, like how these two fields are really related. because as I am working in radio astronomy, so maybe I can tell something more about radio astronomy. Then I will no, because I'm not much more about medicine, but it has really large application in the medicine. So this is a radio telescope, and this is a single dish radio telescope. As we know, the wavelength of the radio telescope is more millimeter to kilometers, so that's why we need a single dish. Is it is not similar to our optical and IR telescopes or UV telescope. It really need a dish which we are using for our TV communication, or maybe dish TV, or maybe radio, something like this. Then the electromagnetic rays are coming here, and they are just reflected back to the receiver, and they are taken through the amplifier, and then we are imaging through our computer. The thing is, the important thing to note here is radio signals are really very weak. They are even 10 to the power minus, or maybe in the order of 10 to the power 20 or 10 to the power 15 times less intense, or maybe less energetic than the other electromagnetic spectrum. So that's why we really need a good technology to receive those signals. A fun fact is, the amount of radio signal we received through the last century, if you gather all the signal, and if you want to convert to the heat to rise the temperature of a one cup of water, then it can't rise a single a 1 degree of 1 degree extra temperature, or maybe what I mean to say is, using those signal you can't raise even if 1 degree temperature to a cup of water. So those are really very less energetic and very faint emissions that we are detecting from the cosmos in various objects. That was the schematic diagram of a single dish radio telescope. So this is the largest radio telescope till available in the humankind. It is the first, which is whose diameter is 0.5 kilometer, and it's a single dish telescope, and it's situated in China. Maybe I wrote China is wrong. Sorry. So I think I made a mistake there. Let me check. Just a second. So yes. Now, sorry for this. I will do this again. So now this telescope, which is visible to us, is a 2-element interferometer. Interferometer. I will tell what is interferometer, and I will tell why we require interferometer in 2 slides. Because the size of the radio wavelength is very large, so that's why we can't make such a big telescope every time. So we have to do something that we can capture. So what radio astronomers do, because they really made a new invention, that they combine 2 telescopes at a time, and they are giving signal to a single receiver, and they are capturing the radio signals through the both telescope as they are working as a single. So which is called the interferometer. It is one of the popular term in radio astronomy. So basically I can say that how can I say simply is, we have 2 eyes, right? We have 2 eyes, but we still see a single object. It is something like this, like it's not exactly like this, but something like this. You're just focusing on a single object, but now the field of view is really large. You can really grab a big amount of sky at a time. So now, so now if you see here, this is two telescopes, and when there is two telescopes working together, then we called it as a baseline. Maybe there are multiple telescopes, there may be a multiple baselines for each combination, and this is a website coming, and this is the time delay, and we are correlating the signal, and we are getting the good image of the radio source. So now to this. So this is very large, very long basin interferometer, BLBA. Because I still did not tell that how far should be two telescopes. The farthest telescopes, like how far they are, that is known as the size of the telescope. Like suppose there are two, like in previous case, suppose there were two telescopes, and maybe they were 200 meters separate away, and they act like as a 200-meter telescope actually, even if each one is only 25 meter maybe. So here the very long basin interferometer is like there may be telescopes throughout the globe in different countries, and they really act like a single telescope as large as the Earth. Yeah. So now this is an example of interferometer, which is the very large array. You can see there are more than two antennas, and they are acting together, and they are really work like a single telescope. The largest baseline in the VLA is 35 km. So I will show a small presentation that how the VLA is configured. Just a second. I'm sorry, I don't think this one. I think this one. Yes, if you see here, because each telescopes in the VLA, they are moving through a train, or maybe through a railing, and they are changing their position, and they are making in different configurations. Maybe sometime bigger maybe sometimes 10 kilometers, sometimes 1 kilometer, or sometimes even 15 kilometer, or something like this. They have 4 configuration in VLA, and if you see here, there are total 4. Yeah, so now coming to next slide. Yeah, so now the we knew something about the radio astronomy, that why we really need more number of antennas instead of one antenna. So here you see the both radio astronomy and medicine disciplines require high resolution and accurate and detailed imaging. Perhaps the most notable example of knowledge transfer between these two studies is the technique of aperture synthesis. So if you just see here in the video, because if you see, when the number of antennas are increasing, the imaging technique is really going better and better. It's because yeah, if you see here, there are one baseline. Sorry, there is a one baseline, but there are two antenna. So when we are putting more and more number of antennas, it will enhance our imaging technology. And if you see here, the image is really coming visible more and more way. So now there are 6 antennas, and there are 3 antennas, and there are this number of baselines, and yeah, and when it is increasing, you are getting good images. And so radio astronomers are getting good images using interferometer through the aperture synthesis technique. So yeah, so this is really a good technique that you need not to make a very big telescopes, and by making limited number of interferometer, no sorry by putting limited number of telescopes in the interferometer and making limited number of baselines, you can really image the sky better. So this technique is really used in the medicines and to image things. So yeah, so the aperture synthesis technique was developed by the radio astronomer who won the Nobel Prize, Martin Ryle. So this technology is used computerized tomography and magnetic resonance imaging (MRI) and also positron emission tomography, and in many other medical imaging tools. So there is another point I want to say, that the contribution to the medicine sector from the astronomy is the clean working areas, because manufacturing of the space-based telescopes require extremely clean environment to prevent dust or particles that might obscure the mirrors and instruments on the telescope, because we have to deal with carefully, otherwise we will invest a lot of money and it is going to destroy it, because it will not give any result to us. So that's why astronomical developments are always require a clean working area, which is the clean the same thing we may need for our we need for our medicine system also. Like while you are developing a drug, while you are developing a drug or maybe a vaccine, or maybe some other type of any type of medicine, we really have to careful and we have to really need a clean room. So that is also a measure given to the medicine field. So now coming to the everyday life. So yes, so there are many things that people encounter on the everyday basis that were derived from astronomical technology. The most commonly used thing is the wireless local area network. It was developed by John Shubelin, but the initial problem was when he developed Wi-Fi. So when he developed this, the initial problem was how to transfer this to larger distance, or how to make it intense, or maybe not intense, how to make it good amount of signal so that everyone can access. So that problem was solved by radio astronomers, because radio astronomy is always challenged by the faint emissions to how to detect them, and that technique was used in this field, and that was developed, and now we are using Wi-Fi everywhere. So yeah, so second last maybe. So because the general relativity was discovered by Albert Einstein in 1916, about 100 years ago. At that time we didn't know what was the application of the general relativity apart from the fundamental science, or apart from the fundamental discovery in the universe, that how universe works and how time and space work. But the global positioning system is the straight application of general relativity. Without general relativity, we can't apply the GPS, and you know that we have GPS in almost every devices to pinpoint locations, because this n number of application to our life, and without general relativity we really can't do global positioning system or GPS in a good way, and the entire system will be doomed. So some other development is like the interactive data language, which is used in General Motors to analyze the car crashes, and there is a software called IRAF, image reduction and analysis facility, which is used by AT&T Bell Laboratory for analyzing the computer system and solid-state physics graphics, because IRAF is used in optical astronomy, UV astronomy, and IR astronomy to reduce the images and to reduce the spectra of the images. To reduce the spectra from the sources. And yeah, so in the field of communication, radio astronomy has provided a wealth of useful tools, devices, and data processing methods. Many successful communication companies were originally founded by radio astronomers only. And the last thing is the atomic clock, which is developed in 1955, which was calibrated using astronomical emphasis and ephemeris time, a former standard astronomical time scale adopted by the International Astronomical Union in 1952. So this is agreed by internationally, and we get the most accurate time from this clock. So now coming to end of this talk, that we have seen some examples of impact of astronomy in different technology and different branches of science and our everyday life also. But apart from this, there are many good books which is sold over million of copies in the worldwide. One is the A Brief History of Time, which is for a non-astronomer or non-physics background, non-astronomer background person can really read this book, and he can really understand the mysteries of the cosmos. And there is a television series which is called The Cosmos: A Personal Voice, which is by Carl Sagan, and which has been watched over 60 countries and more than 500 million people, and it is really a good series. And many non-astronomers also engaged in astronomy during the International Year of Astronomy 2009, and which is the largest education public outreach event in science. So it reached over 148 countries. So the last thing, yeah. So to feel about the astronomy, I will show this image, because this is moon is rising, Earth is rising while you are looking from the moon. This photo was taken by an Apollo astronaut, and this become a new icon or maybe new consciousness, an icon of new consciousness, because we have seen from our Earth that sun is rising, moon is rising, stars are rising, but this is really a good image, and which look really beautiful, like how you are looking toward your home from the when you are in a different planet, in different place in the cosmos. So yeah, so astronomer Carl Sagan realized the next step to the process. We know about our satellites are coming farther away from the solar system, going farther away from the solar system. So Voyager 1 is one of that solar system which left the interstellar medium, interstellar medium of the solar system, and which is entering, which already passed the Pluto, and this is the Voyager's last look toward the Earth. And in this image, Earth is nearly around 4 billion miles away from that image, and Voyager 1 look toward the Earth. And yeah, so I'm ending my talk. Please ask some questions. You can read this one, and I'm ending this with this video. So yeah, I will wait for questions, and I think maybe, I don't know, the sound is audible properly coming or not, because the video is playing, which is the pale blue dot, famous pale blue dot by the Carl Sagan. I think I am too slow, but yeah, it's okay. So now I'm waiting for question. I'm muting myself to see questions. So maybe I can see questions from here only. It's not properly coming in my mobile. Let's go and check some questions. But where can I check my question? I have to ask him. I don't know why it is asking. Finding the video. Maybe you guys can ask questions, or maybe you can suggest something more. If I am, maybe I might be wrong somewhere in some parts, because I'm just digging out those things, and maybe you can suggest so many other things if you know that radio astronomy given to the world in comments, or maybe you can ask questions that any thing that you didn't understood during my talk, that how technical things is happening in this field of astronomy. Maybe this will be better also, or maybe you can suggest something that maybe I can, because which I'm planning to give a second series of this talk in maybe next month, or maybe 1 month or 2 months after. But maybe you can suggest what you want to listen and all. And yeah, I'm waiting for the questions. By the way, thank you guys for joining us, and yeah, I'm still here. If I'm audible, ask some questions. So I'm not. I think I have to stop here, because my time limit is going to reach. And maybe if you have any doubt, any suggestion, any comment, just let me know, and comment here, or ask in our, or post in our group, or in our group and in our page, and we'll love to answer your questions, because we love astronomy. That's what. Thank you all for joining us, and thank you. Bye bye. Take care, and yeah, have a nice day.